Alright guys, we're going to start off with a little bit of review of graphing an exponential function. Glad to be back on here, believe it or not. I'll apologize if there's any random sounds from the chair I'm sitting in. I'm sure some of you will think that I've got an upset stomach. Just kidding. So we're going to take a look at graphing this exponential function. So before the break, we talked about taking a exponential function and finding the graph by focusing in on specifically what we call, and we've done this all year long, called the parent function. 2 raised to the x power would be what we call the parent function. So if we graph that one first, then we can do the -2 and the +3 using our transformations that we learned well back earlier in the year. So y equals 2 to the x, if I make a table of values just for that part, plugging in -1, -2, 0, 1, and 2 there, and I'm sorry I said that backwards. You plug those numbers in, you just take out your handy dandy calculator, whether that's Desmos or if you've got a TI calculator, and you type it in. If you want to take 2 and raise it to the -2nd power, then I go over here and I use my little a to the b power, raise it to the -2nd power, and it will tell me that that is 0.25. And so then I just go down through the whole process here, raising my 2 to the powers for x. So 2 to the -1st would end up being 1/2 or 0.5, because remember what the negative exponents do, they flip this guy upside down. 2 to the 0 power is 1. 2 to the 1st power would be 2. 2 to the 2nd power would be 4. So I plug those numbers in and I plot those points. If I have that now, what I should be able to do, if I can get this guy, it's not wanting to graph for me. Let me see if I can get this. Oh wow, of course. It's not going to work great. First recording back from spring break. I believe it's on spring break still. That's not ideal, but we'll use this this grid. It'll work. So if I go to plot those points on the graph, and we will take this like this, and I'm going to actually use the big darker marks for my points. That way it'll make it a little bit easier to see. I know that's pretty ugly on the screen there. So if we take -2 and 0.25, and I plot that point, it's going to be about right in here somewhere. -1.5 would be about right here. 0, 1 would be here. 1, 2 would be here. And then 2, 4 would be here. And you see that characteristic exponential curve like we talked about. And the fact that you have now this exponential curve also, we talked about the fact that there's something called an asymptote at the bottom, meaning this graph gets closer and closer and closer to the axis down here, but it never touches it. There are some graphs in the next chapter that we'll get to. We probably will not graph them only because they are way, way too ugly to graph if we're not in person. And what you'll notice on those when you get into pre-cal is you'll see some graphs that have a lot of asymptotes, and you'll even have some that can touch or cross the asymptote, but by definition, an asymptote is a line that the graph approaches or gets closer to out towards the ends of the graph, typically. So that is our exponential graph. But here's the problem. That's 2 to the x. We had 2 to the x minus 2 plus 3. So we're now going to use our skills that we earned all the way back in the very first chapter of our textbook, all the way back from the 2nd chapter this school year, where we took and used that -2 and that +3 to transform the graph, to move it across the graph. And so if you'll remember, we had opposite, same, and this one moved it right to, and this one moved it up 3. So we take every single one of these points and we move them right to, up 1, 2, 3. Right 2, up 1, 2, 3. Right 2, up 1, 2, 3. And that one's going to be on the same as that point, so we'll have to be remembering that a second. Right 2, up 1, 2, 3. Then this one, right 2, up 1, 2, 3. So now our graph has been moved right 2 spaces, up 3, and our asymptote has also moved right 2 and up 3. And typically, you will see, as you get into further parts of math, the asymptote is typically drawn with a dashed line, so you know where it's at. It's not a requirement necessarily to draw the asymptote as a dashed line, but it does help you kind of manage the range of your graph specifically on these, because that means it will not go below that line. Okay, so we're going to be taking a look at some new stuff today. And I'm going to, as I mentioned on the Schoology announcement, I'm going to try to make sure that we just kind of break it into small pieces. We do maybe a couple lessons a week, maybe sometimes just one lesson, especially those weeks where you may have a test. And I'm going to try to give you plenty of opportunities to get with me on WebEx, to ask questions if you have any. And guys, I can't stress to you enough, there's plenty of extra review videos of mine that you can watch, as well as you've got to ask me questions. You can't just sit at home by yourself, and I know this is tough. I know this is a weird situation, but you can't just sit at home by yourself and expect to magically learn it. I'm making the videos to try to give you the opportunity to be able to go back and forth and rewind and watch them again and take notes and watch them multiple times if you need to. And, pause it when you need to, things like that. But ultimately, you still need to have some interaction with me. So don't hesitate to come onto the WebEx meetings that I offer. And I offer them at various times to try to accommodate different people's schedules, because I know everybody's got a weird schedule going right now. But I also can be available if you set up a time with me if you need to. So we're going to be taking a look today at the other side, or what you remember from the last chapter as the inverse of exponential functions. This inverse is called a logarithm. So I want to first of all start off with an example of why you would want to know what a logarithm is in a real world situation. And one of the examples that we looked at previously in the previous chapter, previous sections, I should say. So earlier, before spring break, we were talking about things like a bank account. And I'm going to use a basic example here just to kind of guide in and lead into what we're talking about. So let's say we have a bank account that we want to start when we leave high school, because we paid attention to Mr. Harrison's lessons on, putting money into a bank account and earning some extra money. So we take $2,000 that we get when we graduate high school or when we graduate college, and we put that money into a bank account. So we find an online bank account that gives us 1.5% interest. And that's not very high, but that is basically normal for a online bank account. And if you're looking at a savings account at a bank around here, around Pickens, you're not going to see anything that's that high. So we deposit that money into that bank account at 1.5%. So the function that we learned before spring break is an exponential growth function that said you have the beginning amount, and we could use C or we could use A, multiplied by 1 plus the rate raised to the time, or multiplied by B raised to X. Either way, both of these mean essentially the same thing, but the one at the top is a little more descriptive of how we would actually set up our function. What we would actually do here is y equals 2,000, our beginning amount, 1 plus the rate, which would be 0.015, And typically, I told you guys that's the biggest mistake that most people make is they take that 1.5% and forget to change it to a decimal. You got to change it to 0.015, move your decimal place 2 places. And then it's raised to the t, or the time power. Now, you can also simplify that just a little bit by adding 1 and 0.015 together to get one base there, raised to the exponent t. But you don't have to do that, but it is kind of helpful when we get into this next section that we're talking about. So when we look at this bank account, we could take this equation now and we could find out, okay, how much money am I going to have after 10 years? And so we took out our calculator and we said, okay, I take $2,000 and I take 1.015 and I raise that to the 10th power for 10 years. That means after 10 years, I'll have $2,321.08. So we looked at that and we said, okay, that's not bad. $2,321.08 is pretty good. We didn't have to do anything for that money. We just left the money in the bank and we got interest on it. So fantastic, great. But let's say we've got a sort of different scenario here. Let's say that we want to find out when we need to, or how long, let me rephrase that, we need to leave the money in our bank account until we will have a certain amount. Maybe our goal is to get this bank account now to $3,000. So our goal is to get $3,000 in our bank account. Okay? If that's the case, what I'm asking you to find now is not the amount that you will have after a certain number of years, but the number of years that it will take me to get to a certain amount. And that's where this new function that we're talking about comes into play. Because what this would do is this would be actually giving you a y value, not a t value. It would be giving you a y value, and you would have to solve this equation. Now, I'm going to kind of give you a little bit of preview because we'll actually be solving these equations a little bit later in the chapter as well. But what you would essentially do here is, because this 2,000 is multiplied in the front, is you would divide both sides by 2,000. And so you get 3,000 divided by 2,000, which actually ends up being 3 halves, or 1.5. And then you would have this base raised to this exponent equal to this number. So what you would be looking for, what you would be trying to find, is what exponent should I use for t to get to 3 halves, basically. What should I raise 1.015 to get to 3 halves? So now, while that sounds like, oh, I get it, Mr. Harrison, I just plug in a bunch of numbers for t until I get the right answer. Yes, that would work. But in math, obviously, mathematicians are always looking for a quicker way to find the answer. And so what happened is they started doing some study. Like I said, it's not some guy sitting around, little nerd sitting around in a room like Mr. Harrison is right now in his bedroom recording this. There's not a little nerd in a room sitting around doing math. What that mathematicians did is they just studied and figured out a way to solve this more efficiently. And what they, I hate to use these words because you guys always like to use these, what they came up with, even though technically it was already happening in real life, it's just how they studied it and discovered it really, is something called a logarithm. And what a logarithm is used for is it's used to help you find this missing exponent that we see. So the opposite of exponential is going to be logarithmic. Now, most of you would kind of look at this and think, oh, that's kind of like what we did in the last chapter. No, it's not. We did the opposite of squaring something is a square root. The opposite of cubing something is a cube root. But you don't have a t root. And so what we're going to be looking at is actually something that helps us find this missing exponent. So the opposite of exponential is actually logarithmic. And so we're going to be taking a look at logarithmic functions. So you may want to copy the definition of the logarithm on this page here, but don't copy the top part of this page. Okay, so hopefully you've had a second to copy the definition if you need to. Again, pause it if you need to. Logarithmic functions. So you know that 2 squared is equal to 4. If you don't know that, you can type that into your calculator. 2 cubed is equal to 8. However, what value of x does 2 to the x equal 6? Because 2 squared is 4, 2 cubed is 8, but 6 is in between those two numbers. Essentially, guys, that's what we were talking about with that example that we did with the bank account just a minute ago. What exponent do I need to raise 1.015 to get to that 3/2? That's a lot more complicated than maybe 2 to the x equals 6, but that's the same concept. What exponent do I need to raise 2 to, sorry the way that sounds, to get 6? Like I said, we know 2 squared is 4. We know 2 cubed is 8, but 6 is in between those two numbers. So what does that tell me about the exponent for 2? That tells me that the exponent would have to be somewhere between 2 and 3, right? So yes, I can probably get a pretty good example, and most of you would probably say 2.5, and you'd be pretty close. The exact value is actually found using logarithms. And if you look down here at the bottom right of that paragraph, I've given you that example. The exact answer for that logarithm looks like this. So now what we're going to do is we're going to talk about what is a logarithm. What does it mean? What is that saying right here? What this is telling me is that this value for x right here is log, and this is the way you say it, base 2 of 6. And it's approximately 2.585. What it literally means is that if I take the base 2 and I raise that to the 2.585 power, I'm going to get 6. Now, obviously, it's not perfect, but 6.0001 is pretty close to 6, right? So what we are looking at here is a way to find this missing exponent when we have what we consider an exponential equation. Now, obviously, we're going to come back to that a little bit later in more detail, how to actually solve exponential equations. But right now, we're going to define what a logarithm is. Right here in the middle of the definition of a logarithm is the key thing you need to know right here. And you will hear me say this about 9 million times over this video, and over the next video, and over the video after that. The definition of a logarithm. So I'm going to read out the formal definition of it, but then I'm going to give you what I think is going to help you the most as well. It says, let b and y be positive numbers. B is not equal to 1, so we don't do this with a base of 1. The logarithm of y with base b is denoted by log base b of y, and that's how you say this, log base b of y, and is defined as follows. Log base b of y is x if and only if b to the x power is equal to y. That's a lot of mumbo jumbo, Mr. Harrison. What in the world does that mean? Let's break it down again. And I know I'm going to write the same thing again, but I want to break it down for you. Log base b of y is equal to x if and only if b, this base, raised to the x power, this exponent, equals this number, y. That's what that's saying. Log base b of y is equal to x if and only if this base raised to this exponent equals this number. And what that means, guys, is that when you get an answer to a logarithm, it's telling you the exponent that you put on the base to get the y. So let me go back up here. Log base 2 of 6 is telling you that if you take 2 and you raise it to this power, you will get 6. That's what a logarithm is helping me find. A missing exponent that you raise the base to to get the number on the inside of the logarithm. Guys, that definition of the logarithm is going to be the thing. If you know it, it will make so many things with logarithms become so much easier. It's not going to tell you everything about a logarithm, but it's going to be so important. So you will hear me say it numerous times. So I'm going to say it one more time even now. This base raised to this exponent equals this number. Base b raised to the x power equals y. That's the definition of what a logarithm means. And we technically could go backwards as well. We could say if we know b to the x equals y, this if and only if means that I can also go backwards. If I know that b to the x power is equal to y, then I know that the log base b of y is x. And that's how we actually use it to solve equations that look like this guy over here or this guy right here. If I want to solve those equations, I can actually use the logarithm to find that missing exponent because I can write it this way or I can write it this way. And so the first thing we're actually going to practice is we're going to practice writing something and taking something from one form to the other, taking it from logarithmic form to exponential form or exponential form to logarithmic form. Again, here's the key. This base raised to this exponent equals this number. Say it again. This base raised to this exponent equals this number. So that's the first thing we're going to practice, is rewriting them from one form to the next. So you may want to take a second, copy these down, and then I'm going to do one with you, and then I'm going to let you try the others before I go through them. So I'll give you a second to pause the video here and copy down. Then what we're going to look at is doing an example together. So look at the first one, A. Log base 2 of 32 equals 5. Now that is already answered for you. That logarithm is already written out for you. What we're going to do is we're going to change it or rewrite it into exponential form because we are practicing the definition, and it's going to help us with some other problems as we go through logarithms. So what does the definition of a logarithm say here? It says this base raised to this exponent equals this number. So let's rewrite that. 2 is the base, raised to the 5th power, that exponent, equals that number inside the logarithm. 2 to the 5th power is 32. Now, is that true? Absolutely. If you take 2 and you raise it to the 5th power, you will get 32. So that is what a logarithm is saying. The answer to a logarithm is actually the exponent. And that is critical to understand about logarithms, is that the answer is the exponent. So what a logarithm is mainly used for is for those situations where we want to be able to find a missing exponent, like our bank account example that we did earlier. Logarithms, by the way, are also used in things like the Richter scale to figure out the magnitude of an earthquake. So, take a second and see if you can do the other 4 here. All right, so hopefully you tried them. So let's take a look. Log base 5 of 1 is equal to 0. Now I know that looks kind of weird because I just told you that an exponent is the answer to the logarithm. But think about it. What the logarithm definition says is this base raised to this exponent equals this number. So the base 5 raised to the 0 power is 1. If you'll remember, that's what we said. We said anything raised to the 0 power is 1. And so here's the cool thing. If you have a logarithm of 1, it doesn't matter what the base is down here. You take the logarithm of 1, you're always going to get 0 for the answer. And we're going to talk about that. That's a special logarithm value that you just need to know and have it memorized. The next one is also a pretty special one. Log base 10 of 10 equals 1. The base 10 raised to the 1st power is 10. This base raised to this exponent equals this number. And that should also make sense. 10 to the first power is 10. The next one, this base 10, raised to the negative first power, is 0.1. Now that one's a little bit harder to notice, but 10 to the negative first power is 0.1. Remember what 10 to the negative first power does is it moves the 10 down to the bottom. And so 1 over 10 is 1/10 or 0.1. Or you can use your calculator and just go through. Let me delete these other ones we've had on here. 10 raised to the negative first power is 0.1. So again, this base raised to this exponent equals this number. That's the definition of a logarithm. The final one here, we have 1/2 as the base. So 1/2 raised to the negative first power is equal to 2. Now that one is also a little awkward if you think about it, but remember 1/2 to the negative first power is going to take this 1/2 and flip it to 2. So this base raised to this power equals this number. This base raised to this exponent equals this number. Guys, I'm going to repeat it, like I said, 9 million times. It's going to get on your nerves. You'll be okay. All right. So the next thing we're going to do is go backwards, where we have the exponential form, and we write it into logarithmic form. Take a second, pause the video here if you want to write these down first. Now that you've written them down, let's do one together. Now I did kind of write some of these a little backwards to kind of throw you off a little bit and make sure you're understanding the definition. 729 is equal to 3 to the 6th power. That's exponential form. And that's true if you take out your calculator and you did 3 raised to the 6th power, you would get 729. But what we want to do is we want to say, okay, what does that look like in logarithmic form? Because this is going to be the key thing, being able to write back and forth with that definition of what a logarithm means is going to be the key thing that helps me solve and figure out how long do I really need to leave my money in that bank account. So this base raised to this exponent equals this number. Now say that again, but write it like this in logarithmic form. The base 3, okay, so that's the base on my logarithm, raised to this power 6, remember the answer was the exponent, equals 729. That's the thing that's inside the logarithm. Now sometimes you'll see parentheses around that 729 to help you know that it's actually inside the logarithm, and that might be helpful for some of you. We'll get into that a little bit more when we get into some that are a little bit uglier in particular than the ones we're looking at now. But this base raised to this exponent equals this number, always. That's the definition of a logarithm. The base 3 raised to the 6th power equals 729. All right, so try the other 3. Pause the video there. Okay, so hopefully you paused these and you tried them. But let's look at the answers. This base, 1/2, raised to this exponent equals this number. Think about that, guys. 1/2 to the 3rd means 1/2 times 1/2 times 1/2. That is going to give you 1 over 8. 2 times 2 times 2. So this base raised to this exponent equals this number. So what a logarithm definition says is log base 1/2 of 1/8 is equal to 3. Remember, this base raised to this exponent equals this number. The answer to a logarithm is the actual exponent that you put on the base to get the number inside. So the next one, 5 squared is 25. Log base 5 of 25 is equal to 2. 5 squared equals 25. This base raised to this exponent equals this number. I told you I was going to say it about 9 million times. I know it's getting on your nerves, but I'm going to keep doing it. The last one, log base 10 of 1 equals 0. This base raised to this exponent equals this number. This base raised to this exponent equals this number. 10 to the 0 power is 1. So that's the definition of a logarithm. That's how a logarithm works, definition-wise. Now what we're going to do is we're going to use the logarithm. We're going to learn how to find answers for the logarithm. We're going to learn how to use that definition in our head and use the calculator a little bit. And then I'm going to teach you specifically how to work with the calculator. In particular, if you have the graphing calculators or the TI calculators, there's some buttons that you need to know about. So we're going to take a look at answering logarithms. And then as we go and we learn more about them, next class we'll look at how to actually do some properties of logarithms. I will briefly mention in this video a few things about logarithmic graphs, and I will briefly mention some things about inverses, but we'll come back to those a little bit later when we do equations also. Specifically with graphing on these, we're not going to take the time to graph these in huge detail, but I am going to talk about how inverses tie together with that. So what we're going to do first is actually just talk about a few logarithmic answers. How do you find the answer to a logarithm? So I have these 4. If you want to pause the video here and try these, you're welcome to do that. Remember, it's this base raised to this exponent equals this number. But Mr. Harrison, there ain't no number over there. You're right, because that's what we're doing now. We're trying to actually figure out what the answer is. It's not one of those where Mr. Harrison gave you the answer. So we're just trying to figure out what is the answer to this logarithm. What is the exponent that you put on 4 to get 64? Like I said, if you want to pause it and try them first, you can. You don't have to because I'm about to go through the answers. So log base 4 of 64 means this base raised to this exponent equals this number. But what's the exponent that I put on 4 to get 64? 4 to what power? Right here. Okay, sorry. 4 to what power gives me 64? I don't know. What is it? What is that answer? Well, I could use my calculator to kind of help me out and test it out. I could say 4 to the first power. That's 4. 4 to the second power. That's 16. You know, I could take out my calculator and do that. And I could do 4 squared and get 16. And then I could raise 4 to the third power. And I get, oh, look, I get 64. So guess what? The answer to this logarithm is 3. 4 to the third power is 64. That is what that definition is that we talked about just a minute ago. This base raised to this exponent equals this number. So the answer to this logarithm is 3. So when you're doing some of your homework problems and you're just asked to find the answer to a logarithm, that's what you're looking for. You don't have to do the whole rewrite thing like I have over here, but that's what I'm using to help me understand the answer and help me get what the answer is. Yes, I'm going to teach you how to do some calculator work as well. Just hold on, be patient for a second. Number 2, log base 6 of 36. So 6 to what power is 36? I hope you're screaming at your screen there. 2. 6 squared is 36. Guys, notice we're not saying 6 times 6 is 36, even though that's what 6 squared means. We're saying 6 to the second power is 36. That's why the answer to a logarithm is the exponent, not what you multiply it by. So be careful with that. So, the next one looks really ugly. 81 to what power is 3? 81 to what power is 3? There ain't no way, Mr. Harrison, that don't have an answer. It don't have an answer. Well, you still have to remember some things that we've done in the past. Yes, if you take 81 and you raise it to the first power, that's 81. It's already too big, isn't it? Well, if you take 81, oh goodness, Mr. Harrison, 81 raised to the 0 power, you get 1. That's too low. So what does that mean? If 81 to the 0 power is 1 and 81 to the first power is 81, that means it's got to be somewhere between 0 and 1. That's where those fraction things come into play like we did in the last chapter. And this one's actually a little easier than you think it is, but it's 81 raised to the 1/4 power. How do you know that, Mr. Harrison? How do you know? Because the 1/4 power is the same thing as the 4th root of 81, which is 3. You thought you were going to get rid of those radicals, didn't you? But you're wrong. You still got to know it. So 81 raised to the 1/4 power is 3. Now, like I said, I am going to teach you how to find some stuff in the calculator too. Now, the last one looks ridiculous when you first look at it. Log base 10 million of 1? Mr. Harrison, there's no way I can figure that out. Remember what I said. This base raised to this exponent equals this equals 1? How do you raise something to a power and get 1? Raise it to the 0 power. Anything to the 0 power is 1. So anytime you have the logarithm of 1, you're going to get 0. And so that gives us a couple of special values that we need to know. The logarithm of 1 is always going to be 0, no matter what the base is. Okay, so you're welcome to copy these down, but you don't really have to. Anytime you have a logarithm, doesn't matter what the base is, of 1, you're going to get 0. Log base 7 of 1 is 0. Log base 13, of 1 is 0. Anytime you have a logarithm of 1, you get 0. The other special value is one that we did a minute ago as well on the previous page when we were rewriting over here. The log base b of b. That means if you take the log base 13 of 13, that's always going to be 1. Because this base 13 raised to the first power is the only way to get 13. So log base 7 of 7 is 1. The log base 20 of 20 is 1. So those two values, when you take the logarithm of 1 and you actually take the logarithm of the base number that you have in the logarithm, then you are going to always get that 1. So these two should be some special values that you just essentially always know, that you know those logarithm values. Okay. So here's a couple more for you to try on your own. Pause the video and try these. All right, so 7 raised to what power is 49? 7 squared is 49, so that's the answer, 2. 10, and I'm sorry, that looked like kind of an 11. I'm sorry, I should have said that before I made you go through them. I apologize. 10 raised to what power is 1,000? 10 cubed is 1,000. In case you didn't know that, 10 times 10 times 10 is 1,000. 362 raised to what power is 1? Remember what I just talked about. Anything to the 0 power is 1. 9 raised to what power is 729? 3. 9 cubed. Now the last one actually is going to tie in with our whole inverse concept, but it also just, if you just think about the definition, you can get the answer to this logarithm. And I just want to kind of challenge you a second. 4 to what power is 4 to the 3x power? Listen to what you just said. 4 to what power is 4 to the 3x power? 3x. The answer to that is actually 3x, because 4 to this power, 4 to this power is equal to 4 to the 3x power. They're equal. Now, we're going to talk about that in a little bit more detail when we talk about inverses here in just a moment. So, now, obviously at this point, everybody's thinking, okay, great, I get this, but what if the answer is not so easy, Mr. Harrison? How did you get that one a little while ago, Mr. Harrison, where you had 2 to what power is 6, and you said log base 2 of 6. 2 to what power is 6? How'd you get that answer? You got 2.585 approximately, right? How'd you get that? Or how am I going to get that answer, Mr. Harrison, on my bank account where I had that 1.5% interest raised to the time, and I wanted to find when that is equal to 3/2 because I had $3,000 was my goal divided by the 2,000 beginning amount. How do I get that answer? Do I do log base 1.015 because that's the base of 3/2 is equal to t? Well, yeah, that's how you get the answer, but how do I actually get this, Mr. Harrison? I can't do that in my head. So do I guess and check? No. Here's the good news. On the calculator, there are two special logarithms. One of those is called the common logarithm, and the other is called the natural logarithm. The common logarithm is called that because typically it's used quite a bit. It's the one that you use a lot in probably your chemistry class, or maybe even in physics a little bit, possibly, when you are looking at pH levels in chemistry class specifically. You're looking at acids and bases. You will use a common logarithm. It's a log base of 10. Now, I will warn you, log base 10 typically is not written with a little 10 down here. Typically, log base 10 is written just like that, with a little log and nothing as the base. You need to know that that is base 10. If it is not base 10, it will have a little log base. So if it's base 2, it's going to have a 2. If it's base 14, it's going to have a 14. But if you don't see a base, it is base 10. The natural logarithm is base e. Now, I know we didn't get to spend a lot of time with this guy, but that's that little special number that we used when we were doing continuously compounding interest. You can go back and watch that video if you need to. But the base e is approximately 2.71828182845. That's a big ugly number like pi, sort of. But base e is always going to be written like this. It's called the natural log. Now, I know that's ln. You would expect nl if you're thinking natural log. But I think it has to go back with French, actually. Logarithmic natural. That's Mr. Harrison's pitiful attempt at saying something in a French dialect. So please don't judge me. Natural logarithm is ln. I know that looks like in also, kind of, if you look at it. But it's ln, the natural log. That is base e. Again, if it's base 2, it's going to say base 2. If it's base 14, it's going to say base 14. But if you don't see a base, it's 10. If you see ln, that's base e. So when you see those, when you see log, log of 1,000 like we did a minute ago, that's 10 to the third power is 1,000. So that's why I knew it was 3, because the base on this one is 10. And that's where you got to be careful, because that's the base 10. Same thing for base e. If you see the natural log of, and I'm just going to put 10 here, that is asking me e to what power? E is the base here. To what power gives me 10? Now remember, e, like I said, is 2.7182818284559. The natural logs are always going to have ugly answers to them. So this base is e, 2.7182818284559. Approximately 2.718. So 2.7818 raised to what power is 10? That's what that's saying. That one's hard to do. You can't really do that one in your head. So that's why these two guys are on the calculator, and they are used the most. Like I said, common logarithm is called common for a reason. The natural logarithm is one that is used a lot in natural situations. Continuous interest doesn't work in a bank account typically, but there's a lot of things in real life that grow or even decay at a continuous rate. So that base E shows up a pretty good bit. So when we go through and we use our calculator, we use those two that are on the calculator. Now, I have not done a whole lot with Desmos, so I'm kind of actually learning on the fly as I do this. I'm going to show you the TI calculator. It's more comfortable for me. But underneath the functions here, you should be able to go over, and I believe it's on miscellaneous. Yep, here we go. On miscellaneous, you will see log, and you'll see natural log. So if you hit log, and you put 1,000 in, like we did a minute ago, log base 10, so it's 3, 10 to the third power is 1,000. If you do the natural log, like the one that we did a minute ago, it's underneath functions here, ln, or natural log. We had, I think, 10 on the page there. 2.3025. Typically, 2.303 is what I would round this to. I do typically go to 3 decimal places anytime I answer a logarithm. It's out of habit. It's out of what I was taught. But it's also because typically 3 decimal places gives you a little bit more accurate answer when you're talking about the exponent. Because remember, what this is saying is the base E raised to this power, 2.303, should be approximately 10. Now, let's see if that's true. So I take e. Remember, this guy knows 2.718. This calculator knows it. Raised to the 2.303 power. It's about 10. 10.004. But 10.004 is pretty close. Remember, that's 4 thousandths, but it's off a little bit. Depending on what kind of job you're doing, it may be more important to be more accurate with that. But that's why I typically go to 3 decimal places instead of just 2 when I'm dealing with a logarithm. So again, this base raised to this exponent equals this number. This base raised to this exponent equals this number. But these two are special. The common logarithm is always base 10. The natural logarithm is always base e. The reason I say those are the primary ones on the calculator is because typically for most of us we're using a TI calculator. And this is going to be in a school situation most of the time is what you have. Although with more things going to online, especially right now, you've got Desmos. But on the TI calculator, you can see it hopefully right away over here on the left-hand side of the TI calculator. You have log and you have natural log, the LOG and LN. Now, here's the cool thing about the TI calculator. If you see right here, I'm not going to zoom in on my page here, but hopefully you can see it. Look right above the log here. There's a 10 to the x. That's a reminder that this is base 10. E to the x is also above the natural log. That's base e. So when you do a log of 1,000, like we did a minute ago, whoops, sorry, not 10,000, you get 3 because it's 10 to the third power is 1,000. Same thing with our natural log of 10 that we did a minute ago. It's base e. So e to the 2.303 power is 10. So that's why I say those two are the most common ones that we use. They're on the calculator there. Chemistry class, like I said, acids and bases. When you do the logarithm of the number of hydrogen ions, H plus, I believe it is, the hydrogen ions, you can find out the pH of a acid or a base. And so it helps you out with that. That is where a logarithm is specifically used in a real life situation. But there's several others, like I said, the bank accounts and things like that. So those two are the primary ones on the calculator. Well, Mr. Harrison, that still doesn't really help me out when it comes to how do I get the answer for that one you did a while ago? I'm still wondering. Log base 2 of 6. 2 to what power is 6? How did you get 2.585? Or how do I do that bank account example where I was looking for the 1.5% interest? How do I do log base 1.015 of 3/2 to get my t? How do I do that? How do I do ugly ones like that? That still doesn't help me because those are base 2 and base 1.015. You just told me the calculator only does base 10 and base e. The common logarithm base 10 and the natural logarithm base e. How do I do log base 2? How do I do log base 1.015? Well, guess what? Calculator can help you there too. So let me show you. Let's go back to our little fun math menu. We've used it before for the cube roots and things like that. If you go in that math menu down near the bottom of the list, you see this little log base guy. The log base is going to give you a logarithm, and you can type in any logarithm base you want, and you can type in any logarithm value you're trying to find. 2 to what power is 6? Press enter, 2.585. That's where Mr. Harrison found that answer. That's how I knew 2 raised to this exponent equals this number. So I use my calculator with this little log base feature. You can do the same thing if you go back to math, go down to the bottom of the list, log base, and I could say 1.015. Remember, that's my 1.015 is my 1.5% interest every year. And I was looking for $3,000 with a beginning amount of 2,000. So 3,000 divided by 2,000 was 3/2. Press enter. 27 years, 0.23. What that tells me, 0.233 by the way, what that tells me is the time that it's going to take me, 27.233 years to get to $3,000. If I'm looking for some kind of trip real quick, that normal bank account's not going to help me. That tells me I'm going to have to actually leave my money in the bank account for a long time. Or, if you paid attention to the other lessons that I gave you, those of you that came online, especially for the WebEx sessions, it's more beneficial if you keep depositing money, not just one deposit of $2,000. That's where this time right here can be minimized. Okie doke. So again, what is the logarithm doing? This base raised to this exponent equals this number. So 1.015 raised to the t equals 3/2. So this is the time. So that is where the calculator is really awesome. You can use those logarithms if you have the bases there, or you can use the logarithm that's the base on the calculator. On Desmos, I believe they also have one of those on Desmos. Let me double check and see. Underneath the function menu, it looks like right here, see the log base A right there? If you click on that little log base A, it gives you the option. You could type in 2 and do the log base 2 of 6, 2.585. Or you could go in here like we did just a minute ago with our bank account, 1.015, and then 3/2, 27.233. There it is. So Desmos or the TI calculator can get those bases for you. Now, when I was in school, we didn't have that really cool way of doing that. We actually had to use a different little method when I was in school. I'm going to show you what that method is, although it's not used much anymore, but it's called the change of base formula. Basically, the change of base formula means if you have log base 2 of 6 and you can't find the answer, you can take a logarithm with whatever base you want. You can make your own base up of the number that's on the inside, divided by the log of any base you want of the actual base number here. Now, what would you use? Well, typically, we use log base 10. Or we could use log base E. And if you take the log of 6 divided by the log of 2, it's going to give you the same answer, 2.585, that we got a minute ago. So when I was in school, we didn't have the cool little log base thing on the calculator. So to do log base 2 of 6, I actually had to take log of 6, close my parentheses, divided by log of 2, press enter, and get 2.585 then. Or I could do the natural log of 6 divided by the natural log of 2. Now, honestly, that's actually not a whole lot more button presses compared to the little log base thing that you guys have in the math menu. You can go down to the bottom of the list again and go to log base right there, and then click that in and do base 2 of 6. You don't actually have to use the change of base formula. It still gives you the right answer. But really, it's very similar to the same number of presses of buttons. So honestly, it's just one of those things where it's preference. For me, sometimes I can still do this quicker than actually typing in the formula using the log base cool little thing you guys have on the calculator. I don't care which one you use. I really don't. I do want you to know this formula because I believe there was one situation in calculus, if I remember correctly, where we did still use this little change of base formula a little bit. So I want you to be aware of it, but I'm not going to really test you on this little formula. The change of base formula is just there mainly for older calculators and specifically. So it's how you take and find the log base 2 of 6 if you don't have the cool little calculator technique. All right, so a couple of last things that we're going to talk about with logarithms. Number one, logarithmic functions and exponential functions are inverses of each other. That means they undo each other. So what do I mean by that? Well, remember when we did this whole g of x and f of x thing with inverses in the previous chapter? We said that if two things are inverses of each other, if you do g of f of x or f of g of x, if they are inverses, big if there. If they are inverses, then they will cancel each other out to just x. They will cancel each other out to just x if they are inverses. So what that means for us with logarithms specifically is that if I have a logarithm base b for my g of x, and I plug in f of x into g of x, and f of x also has base b, then the answer to this is just going to be x always. Now look at that closely. This base raised to this exponent equals this. If you look at that closely, it should make sense. B to the x power is b to the x power. And so then we have over here, oh wow, is this thing not liking me right now? Sorry guys, I'm trying to, it won't let me get the pause button on the screen. I was going to pause something, I was going to do something real quick. Never mind, we'll keep on going here. Log base b of b to the x, this base raised to this exponent is that. B to the x equals that. So whenever you have log base 4 of 4 to the x, you get x. If you have log base 13 of 13 to the x squared power, you get x squared. I know that's kind of weird, but that's what you get when you have a base that's the same, because logarithmic functions and exponential functions undo each other. The same thing is true the other way around as well. If you have the base for the exponential function f of x, b to the x, and you raise it to the log base b of x, you get x, because the bases are the same. An exponential function and a logarithmic function undo each other as long as the base is the same. That one's a little bit harder to understand mathematically without some numbers. So let me give you an example. If you had 4 raised to the log base 4 of 16, the answer to that would be 16. But why? Here's the reason why. If you zoom in here and you look at just the log base 4 of 16, 4 to what power is 16? 4 to what power is 16? Hopefully you're screaming at the camera that that is 2. The screen, I should say. Log base 4 of 16 is 2. So the answer to this whole logarithm is 2. Well, if the answer to that whole logarithm is 2, what's 4 squared? 16. So essentially, anytime you have the same base, same base, same base, same base, it cancels it out to just whatever's here, to whatever's here. They are inverses of each other. They undo each other. So that's the last main thing with logarithms that you need to know today. One more tiny little thing I want to mention is about the graph of a logarithm. I'm not going to actually graph one, but because logarithms are inverses of each other, and exponential, and logarithms are inverses of each other. If you have y equals 2 to the x, we did that one earlier. That's an exponential growth function that looks like this with an asymptote across the bottom. If you have a logarithm base 2, that is the inverse of an exponential base 2. That is going to give me, let me change the color here to distinguish between those. It is an inverse. So that means it's going to reflect across. The x's and y's are going to switch. So it's actually going to be a graph that looks like this. This is the characteristic shape of a logarithm because it is the inverse of exponential. Remember, it is going to reflect across this line, y equals x. That's what inverses do. They reflect across that line. You switch the x's and y's, that's what happens. So a logarithm is going to look like this, and it's going to have an asymptote straight up and down, a vertical asymptote instead of a horizontal asymptote. And so that's what a logarithmic graph is characteristically shaped like. It also moves left and right and up and down just like all the other graphs we've done all year long. It can transform. So again, I'm not going to go into big detail on the graphs. I just want you to be aware of the shape of those graphs. And specifically, tie this back to that, our coronavirus situation. If you graph the coronavirus on a logarithmic curve, you can see more specifically how quickly things are growing, especially if things are kind of leveling off. The exponential function can kind of be a little tricky sometimes. It looks very, very drastic, but you can see slower portions in the curve if you do a logarithmic curve. You can also look and see, like I said, an exponential logarithmic function, describes specifically a Richter scale. So as you go this way, more magnitude, it's 10 times as high as on the scale. So a logarithmic curve shows you exactly how a magnitude of an earthquake works. So that's what we need to know about logarithms so far. Next chapter, or next section, I should say, we're going to be looking at some specific properties of logarithms and how to work with logarithms in different problems. So, big key, like I said, is the definition. This base raised to this exponent equals this number. That's the definition of what a logarithm means. And that's why it helps me find a missing exponent. This base raised to this exponent equals this number.